know that we used Reynolds transport theorem to substitute for energy, total energy in the system, and we ended up with some equation. I don't think you need to worry too much about that, but the gist of it is that it's much simpler, I think, than conservation of mass and conservation of momentum, because all the equations we've dealt with are really just one-dimensional. They're streamline equations. And there are two relevant streamline equations that we deal with in terms of energy, and that is Bernoulli, that happens to have a, well, it's written backwards here from the way we normally write it. This is the upstream part. Has to be the upstream part. This is the downstream part. Well, I guess I shouldn't have. Yeah, you know, this has to be truncated there, right? So just get rid of that. And it's important that you do that. It's always written along a stream tube, whatever that stream tube should be. Looks like a brontosaurus. Don't you think? So this is V, well, we've always called it 1, right? V upstream is 1, and downstream is 2, and they're streamline velocities. And so we just need to be cognizant of the fact that we're writing between those locations. So upstream, so I guess in this equation it's shown as in and out, right? My writing isn't getting any better as it goes along. And so the velocities are streamline velocities. They're not in or out. They're just always positive. And so we never worry about this alpha term, which you always take as 1. The magnitude of the pump head, we know, right? The pump head is positive if it's pumping. It's negative if it's a turbine. If it works out that it's a negative number, then you're getting energy out of the system. And it's equal to the power in watts, the rate of doing work, which is why we write it with uppercase W, and it's equal to the volumetric flow rate times the unit weight of the fluid. And so typically pump capacities are defined in terms of power, but this expression, as you know, all of these terms are written in terms of length. They have to be, you have to add apples to apples, and so elevation, velocity head, and pressure head are all units of length. And as we've dealt with later on, so I won't talk about it now, when we talk about head losses are always positive. You can't, it's pulling the bag across the briefcase across the table trick. Pull it one way to get it to one place, you dissipate energy. You pull it back to its resting place, you don't regain that energy, but you lose an equal amount that you previously lost. And so head losses are written in terms of, they're always typically, well, they're always positive, I think. I can't think of any condition when they wouldn't be. So that's the one expression that we have, which we've used for pipe flow as well. And so that's a must, right? This is a keeper, this whole thing. And we'll talk a bit more about it when we talk about pipe flow. And I guess that's this. Yeah, if you, for instance, put this expression in here, you basically get W dot over M dot G, which is equal to W dot volumetric flow rate times density times G. Right? They're all equivalent, so we started using this. Okay, so that's Bernoulli's equation with where we have some viscous losses included in it in this term. So that's one way that we can write the one-dimensional energy equation. The other way that we can write it is in terms of this, where this is the thermal energy in. And so in is positive in the sign convention. Someone shouting at me? No? This is the work, power in, again, is positive. And these are velocities and elevation heads, and mass flow rates are positive always in the system. And what is this? This is enthalpy. Is that right? I think. Again, in and out. And so that's the sign convention for that. So those are the two equations you need for thermodynamics. You don't, and how to use them, of course. Don't need Reynolds transport theorem, although we all know that that's where it comes from, and but we don't need to reproduce that. And so we've used those in a variety of circumstances, and you can look back through the notes for the cases that we've used them in the examples here. And so you can compare the examples here, and so you know what we've talked about in other reviews, and compare those to what have turned up on the exam. So I'm not trying to be disingenuous and drag you off into the wilderness somewhere, but something probably will turn up related to these and related to the examples. So everyone okay with that? So I can roll this off the screen. Yeah. So this is just this, and so we've talked yeah. So this is exactly the same expression, just happens to define it in terms of the different quantities and write it a couple of different ways. And I think we did one example in class with this, and it was this, to basically look at energy going into a system. And so if you're dealing with a question that defines enthalpies in and enthalpies out, then probably the equation you might want to be using is this expression. And so if that happens, so we really only used it in this one example. And so this isn't a thermo class, but this is our brief foray into thermo, I guess, in terms of at least looking at cycles, I suppose, right, in terms of some of it. Okay. So that's one of the expressions. So this whole part that we did on the energy equation, which is really just the Bernoulli equation with losses in it, revolved around using these one-dimensional equations either for enthalpy, which we've just talked about, or just using Bernoulli. And you just have to be able to take the cues that you've used in the other stuff on Bernoulli and translate these code words in your understanding of the problem. So when you have to decide where to write the equations between. And you could, of course, write this equation anywhere you wanted here if you want to. So this is the question we did in class, looking at transferring water between two tanks and looking at calculation. I'm not sure what we're trying to calculate. We're trying to calculate flow rate. Yeah, some flow rate Q. I guess I should look at the bottom. Yeah, calculate the flow rate that you get for pumping if you have some particular pump that would have either a head or a wattage attached to it. In this case, it just happens to be a head which is defined relative to the flow rate. And so, in other words, if you're pumping a large amount of fluid, you can only pump it up a small amount. It's like torque on a car, right? I guess in some respects. And if you're pumping at a very slow rate, then you can actually provide a lot of power to get stuff elevated to a large height. And the physical meaning of this is that basically you're pumping a very small, at this limit of this pump, you're pumping it up 200 is it meters or feet? Is it metric? Is it feet? Okay, 200 feet, yeah. Yeah, I guess I see that just. So it means that you're barely pumping it up from one location to 200 feet higher into an empty tank is kind of the interpretation of that. And of course this means that you're pumping water at 2 cubic feet a second, but you're barely able to raise it up more than a fraction of an inch. So that's the physical meaning of what pump head is. And so you need to write the equation at 2 points. Write it upstream, since the fluid is going through this way, I guess. And you could write it at the bottom of this tank. You could write it at the bottom of this tank. You get exactly the same results, but it's easy to write here and move between these elevations. And so in this case, atmospheric pressure at these allows you to get rid of these two. The elevation between them means that the difference between these two, I guess, is 100 feet. The big tank, if you ever see large tank assumption, then this means that the velocity at these locations should be 0. and so get rid of that. And we'd have some losses defined in terms of this parameter here, v squared over 2g. So in other words, head loss is equal to some factor times k sub l v squared over 2g, as we've dealt with in minor losses in pipes. No major losses in this particular case, I don't think. And define HP in terms of this. And so HP just happens to be a function of flow rate. This happens to be a function of flow rate. You have one equation and one unknown, which is flow rate. Solve for flow rate. So that's it. So it's just a matter of providing some clarity to sort these things out in your own mind. And so get rid of the terms you can do. I don't know that you need to, but maybe it's always useful to note that if you need to, the other expression that you might need to think about is continuity, right? Whoops. So whatever goes into this pipe has to come out of this pipe if it doesn't accumulate. And so sometimes if you have one equation and two unknowns, then you can link them together in this. And in some respects you do that here, right? Because this is defined in terms of flow rate. This is defined in terms of a velocity. So I suppose the linkage here is that velocity times area in the pipe is equal to volumetric flow rate. So you need to use that linkage to link those. And the rest is just manipulating the expression, right? So that's one example. Okay. So we've done one example with enthalpy, one example with a pump in it. And so the other thing that we talked about stream tubes and streamlines and how to define those. You note that mathematical stuff isn't in here, but we did talk briefly about flow nets. And so flow nets are straightforward. They've turned up other places. And so the basic idea is that if you take a flow system and you can write the boundary conditions in terms of a total head, which we will call H, which is equal to elevation plus pressure plus velocity head, and you throw this one away, then you can, if you can draw a picture that incorporates the boundary conditions of equipotentials, which in this case would be an upstream equipotential here, and in this case a downstream equipotential here. And if you can link them somehow, I wish I had a different colored pen or could switch colors, if you can link them with a series of streamlines, of which this is one, of which this is one, of which this is one, etc., and this is the bottom one, then you can actually do very interesting things with it. So what you have to be able to do is, if you can draw a net, Spider-Man net I suppose, so that the equipotentials and the streamlines join at 90 degrees. So if you look at every single component of this, they're all joining. They're not quite squares, right? But they're not squares, but they're curvilinear squares. And if you can draw a series of these where each one of these individual components is roughly the same edge dimension. So in other words, well, you see it down here, this length is equal to this width, which you have here, then you can actually do some interesting things with it. And the three main interesting things are that, one, you can figure out what the distribution of head is within any location here. So you could figure out the pressure at any individual point. So you can figure out the head. And you can do that just by counting the number of drops. And so doing this, we've gone through the derivation, so we don't need to do that here. But you can count the number of drops. So from the upstream, so this is, if you like, you could imagine that on this upstream, if this was just a vertical face, then you'd have the fluid pressure that would equal this amount. So the question is, why is it a constant head? Well, it's a constant head because if you take any point at this here, and you look at the elevation of that point, and if you look at the pressure head at that point, the sum of those two magnitudes at this point adds up to this value of h. If you do the same thing here and calculate the elevation of this point, which is higher, and look at the pressure of this point, which is lower, the two of them still add up to the same amount of the head. So the upstream boundary is a total head boundary, if you like. Likewise on this side here. If you look at this elevation here, it has a certain pressure acting on it and a given elevation relative to some datum. And if you look at this point here, the pressure is 0, but the elevation is larger. And so along this line as well, they both add up to this single value. And so if you wanted to, I suppose you could think of this, maybe it's easier to think of it this way, as it's just a stream tube. It's kind of a random stream tube. It has this magnitude at the upstream side, and it winds through this thing, and it comes out at the downstream side. And along this, it has H0 and H1. And also, as you go along here, it's kind of divided up into these squares. So all I'm doing is I'm taking out a stream tube, and I'm going to count the number of drops that occur along it. So in other words, if I wanted to calculate what the head was at this middle point, it would be what? Well, what we know is, by definition, each of these, I'm going to come back to it, each of these, as we go from this equipotential to this equipotential, we've dropped in head a certain amount. As we go from this one to this one, we've dropped the same amount, which we don't know. But if we know that in going from here to this point here, we go from 1, 2, 3, 4, 5, 6, 7, 8, 9 drops, then we know that the head change between this place and this place is 1/9 of the total head drop. And so you can use that to be able to figure out exactly what this is. So I don't know if I did 9 here. So this is drop, so number of drops. 0, 1, 2, 3, 4, 5, 6. Well, I did. I didn't think about that, but I must be smarter than I thought this morning. Always a bonus. So the 9 drops. And so if we wanted to calculate the head at this particular location here, HM is equal to H0 plus the difference in head between those two, which I guess would be H1 minus H0. Right? If this head here is lower than this head, then this will be a negative number. And it's multiplied by the total number of drops. So N drop for HM divided by ND total. So in other words, it would be equal to, just to put numbers in it, the 1, 2, 3, 4, and then divided by 9, right? 4/9. So in other words, you've dropped 4/9 of the head over the length. So yeah, and this is just the change in head across the system. This is a plus, right? So in other words, all it's saying, if you want a physical meaning for it, is that you've dropped 1/9 of the head here, 2/9, 3/9, 4/9, 5/9, 6/9, 7/9, 8/9, 10/9. So by the time you've dropped 10/9, sorry, God, 1, 2, 3, 4, 5, 6, 7, 8, 9/9. By the time you've dropped 9/9, if this is 9/9, then this should be H0 minus H0, so it just should be H1, right? So, and likewise, if you drop 0/9, it should be the value upstream, and it is. So that's the first thing. So one is we can calculate what the head is. Seems kind of esoteric, but if you know what the head is, of course, if you know what the elevation is, you know what the pressure is. So if you know what this is, you know what the elevation is, you can calculate what the pressure would be. So it's quite a powerful method. So that's one calculation. The other calculation is that you might want to know how much fluid is going through here. And so the expression for that is merely to take, well, just an expression. So calculate flow. Flow rate. The volumetric flow rate is equal to hydraulic conductivity, which is in meters per second, multiplied by the change in head, which is this, across the system, multiplied by the number of stream tubes and divided by the number of drops. That's all. Very powerful method. We messed around with it in class and kind of derived it, but all we're doing is we're saying that we can immediately calculate that for this particular example if we know what the magnitudes of those terms are. So if you want to know how much fluid is coming out of this surface right here, and which has to be the same amount which is going into this back surface here, in this particular example, what? If this is 0, if this is 10 meters, if this is 20 meters, then what is it for this example? So Q is equal to hydraulic conductivity whatever it is, multiplied by the head drop, multiplied by number of stream tubes over number of drops. Then it's equal to whatever this is. Delta H is going to be 20 minus 10. And it's going to be multiplied by the number of stream tubes. 1, 2, 3, 4. Number of drops, we already said 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's it. So it's an incredibly powerful technique. So basically, our reasons for looking at streamlines, they're used in a variety of different ways. This is just one application of streamlines, is that if you can draw something that satisfies the boundary conditions, this is an equipotential, this is an equipotential, and is joined by some streamlines with equipotentials that are 90 degrees to it. If you can just hatch that out yourself, de facto, it represents a true solution to your problem. And so it's an important concept in petroleum engineering. It's a method that's kind of grown up in groundwater hydrology. If you're looking at wind forces on turbine blades, you can use it in exactly the same way as well. We haven't used it to calculate forces, but you can. You can calculate pressures, and if you know what pressures are, you can calculate forces, and so you can calculate energy off turbine blades as well. So store that one away for the for either this exam or the next. Okay. Everyone okay with that? So energy equation was Bernoulli equation that allowed us to be able to have losses. Another very powerful method in fluid mechanics is dimensional analysis, which relies on defining non-dimensional parameters. And so we can go, well, moderately quickly through this. It's a very simple idea. The idea is that if you take a model and you do an experiment on it at some conditions, you can take the behavior of that model and replicate the behavior of a prototype just from those model measurements. And it really relies on three main ideas. The main ideas principally are that, well, it relies on one main idea. The one main idea is similitude. And that you can generate similitude between a model and the prototype by doing three things. You can make sure that the geometries are the same. So lengths and diameters and roughnesses and diameters and lengths and spans, as we went into examples on flight, are the same. So in other words, if you're doing the model has to look like the real thing. It can't be stretched or squeezed in some way. It has to physically be reduced in all dimensions. So first is that we want geometric similitude. The second is that we want to have kinematic similitude, which typically means that the Reynolds number of the model is equal to the Reynolds number of the prototype. And typically, so if we have the geometry is the same, so the model is the real model of the real system. If the Reynolds numbers are the same, then I don't think it's here, no, it's not here, then the flow regime around that object is exactly the same in the model as in the prototype. And dynamic similitude would be that the forces acting on the system are the same. So typically these are that the Euler number for the model is equal to the Euler number for the prototype, or in a free surface problem that the Froude number for the model is equal to the Froude number for the prototype. Or the Weber number for the model is equal to the Weber number for the prototype. The capillary number if you're a petroleum engineer. Things we haven't talked about, but there's a whole host of non-dimensional numbers that we could do. But that's basically the essence of it. So I'm coming back to this, but so the idea is embodied, I think, in this figure. So you want to do a model analysis, then you want to make sure that your model looks like your prototype by having the same geometries, not this. If you want the flow regime to look the same in your model and your prototype, then it has to be running at the same Reynolds numbers between them. And if you want in some way to be able to use the forces for lift or the force against your satellite dish, then the final thing is that you want in this case, the Euler number to be the same, or for a free surface flow, the Froude number to be the same. So that's pictorially how that would be. And so if you get the Reynolds numbers to be the same, then you actually only need one experiment to do it, right? Because what you could do is you could do a whole bunch of experiments at different, for instance, Reynolds numbers and measure the Euler numbers. And so for one model, you'd have a whole bunch of numbers. If you do the model experiment, which gives you this number and this number, if this Reynolds number is exactly the same as the model and the prototype, then you only need one experiment. If for a model you do a whole bunch of different experiments, then you can build a curve that looks like this, which is true for that particular, say, geometry of the model. And so it doesn't matter what Reynolds number your prototype is going to work at, because you always have the result for a whole span of Reynolds numbers. But dimensional analysis is really just that. The three tenets. The model has to be a model, same geometry. The model has to be run at the same Reynolds number. And so in other words, you can run a model at a whole bunch of Reynolds numbers and get this curve. And so that when you look at your prototype, you always have the right Reynolds number to get the Euler number. If you have the Euler number, you have the pressures on the structures. Lift, drag, pushing the antenna over, etc. And so that's basically the idea. And so this would be for an example with 2 pi groups, because there's just one length to diameter that you're using. It doesn't change. If you had some with different length to diameter ratios, perhaps you'd have a bunch of curves. But that's basically the idea. So the use of models, remember that. This is just going through that, basically this, making sure the Reynolds numbers are the same. The model's the model, de facto. The Reynolds numbers are the same. If the Reynolds numbers are the same, the Euler numbers are the same. And so you can calculate what the forces are. Okay? So that's dimensional analysis in a nutshell. The other part of it is that you want to judiciously be able to figure out what the non-dimensional numbers are. So even though it's called dimensional analysis, we have a whole bunch of non-dimensional numbers. Geometry is one of them. Reynolds number, the ratio of inertial to viscous forces, is an important one, obviously. And these other two are important as well, for the reasons we mentioned. And we've talked about them. There is a formal way of being able to get those. And so if you look in past exams, there probably will be a Buckingham Pi type question. I'm not sure we have much time here to go through it. But the basic idea is that if you can define just the components that define your system, such as, I don't know, for flow around this dish, some velocity, far field velocity, maybe density of the fluid, viscosity of the fluid, some diameter of this, etc., the pressure that gets applied on it, then there's a formal way to be able to take those variables and to do a couple of different things. One is you can figure out how many non-dimensional groups will describe your system, if you know these variables, and if you know whether mass, length, and time is represented, just by taking the 5 of these, subtracting away the 3 different dimensions that are represented, and then dividing them up into some way in terms of repeating variables and dependent variables. And so if you look at any exam question, just to make it easy for the grader, you get different results if you choose different dependent variables. And so typically in a question, it'll be formulaic in that you'll be told which ones are the repeating variables and which ones are the dependent variables. And it's just a recipe to go through it, and we don't really have time here except to maybe talk about the high points, is that you go through it and you take 3 repeating variables at a time. And so in other words, in this case, the repeating variables are diameter, density, and velocity. And then one dependent variable, which goes out here. And you do the Buckingham Pi thing to it. And so really all you're doing is making sure, the big picture is that when you have these 4 parameters grouped together as products of each other, all you're doing is making sure that the multipliers, the exponents of them, come out so that the dimensions of that parameter are 0. So it has no dimensions. That's really all it's physically doing. And so the formalism is, I guess in this particular case, well, no. So that's not true. So in other words, forget this. So select the repeating variables, in this case, are the first of those 3. And then you have 2 other variables that describe this behavior. We have diameter, velocity, density, pressure, and velocity. And so pressure is used here. Viscosity is used in the second one. So between these 2 pi groups, all those 5 terms are represented. And you just go through this formula where this one is multiplied by 1, and the remainder of these are multiplied by some exponent that we don't know. And so Buckingham Pi, all it does is it gives you the magnitude of these exponents, so that when you multiply this thing out and substitute back these exponents, the resulting term is non-dimensionless, as it is here. And so this term is basically an Euler number, right? You could also write this. This pressure here is a change in pressure over a length. This is a diameter. This is a velocity squared, and this is a density. This diameter and length obviously cancel out as units, so it's a pressure divided by v squared over v. So this is an Euler number. And if you go through this and work this one out, then this also is a number that you recognize as well. It's the ratio of inertial forces over viscous forces. It's just written a different way. And so you can choose different dependent variables and repeating variables, and you'll get non-dimensional parameters that look different, but if you manipulate them, you can always get them to be the same. So it doesn't matter. So if you are given a question that involves this, then you should look at, you'll be told which ones are which. And so it becomes a recipe. So understand two things. Understand Buckingham pi, and then understand how to use the results for the non-dimensional parameters that come out of it, which is what we spent the first part of this discussing. Okay. And we did an example. No, that's stretching. Pipe flow. What is pipe flow? Pipe flow is Bernoulli's equation with the head losses. I guess the only thing that's different to this from what we talked about before, again, upstream, downstream. Again, we know what this is. We've talked about it. And the only thing I guess we have to define slightly differently is that the head losses now are defined in a very specific way. The head losses are defined as a function of minor losses, which we've seen before in the previous example. We talked about the first example we talked about today as a loss coefficient multiplied by a velocity head, and the major losses are defined as a friction factor, a length of pipe, diameter of the pipe, and velocity in the pipe. So I guess the things to remember are typically this is 1, typically this is 1. Remember always that this is the velocity at the outlet, this is the velocity at the inlet, and this is the velocity in the pipe or the fixture. It's important. And so when you're doing the calculations, it's important to realize that. We only dealt with, by the time we closed out on the third class of the 10th week, on type 1 problems, which means we have a flow rate defined. Forget this. Don't need it. Running out of time. And so Moody charts, we know that there are 3 regimes. There's the laminar behavior. Oh, come on. Not time to go yet, surely. Transitional flow and turbulent flow when the friction factors don't change. And it wouldn't be unusual. You don't need a Moody chart. There isn't one in the exam either. So typically, if there is a pipe question, you'd be given the friction factor to use and the loss coefficients, just because it's easier to grade. And there are a couple of examples.